This is video 311, and the goal of this video is to be able to graph transformations of exponential functions. So, exponential functions. F of x equals b to the x. That's the standard form of an exponential function. It's the parent graph. But there's a few restrictions on that. First of all, b cannot be 1. That's the first restriction. B cannot equal 1. Because if b equals 1, that's just silly, because 1 to the x is just 1, no matter what you plug in for x. The second requirement for this function is that b is greater than 0. That would look like the following, this function that you see down at the bottom here. Negative 1 to the x power. Negative 1 to the x power does not behave like these other functions listed here. These functions all have similar characteristics. So this one with the negative 1 to the x is going to, in fact, bounce around positive and negative and all over the place, because a negative to a power will be positive or negative depending on if the power is even or odd. So that does not behave the same way. And of course, another non-exponential function is the following quadratic that you see down here. This is not a function as well. This says f of x equals x squared. It is not a function. It is not an exponential function. It is a function, but not exponential. Exponential functions, the exponent has to be the variable, in our case, x. So the three examples here, 2 to the x, 10 to the x plus 1, and 1/2 to the x minus 1. Those are three examples of exponential functions, and we'll learn how to graph all three of those types and some other additional forms and transformations of them. Let's start with this. First, understanding a few things about exponential functions. Here are three parent functions. They are varying values of b, where the function is b to the x power. And so the variables of b are listed there. I want you to see if you can find one or two different characteristics that you know they all have in common. They all have something similar. Think about that, and then we'll summarize it. One thing you should be noticing is that they all cross right at that one point. 0, 1. The second thing you should notice is that they all kind of get really close to the x-axis. So it looks like they have a horizontal asymptote. They all get really close to the x-axis. Some of them go to the x-axis as x gets really big. These do. Then you'll get closer to 0. These go when x is really small in the negatives. But either way, they all have a horizontal asymptote at 0. So let's first investigate that. The parent function will have a horizontal asymptote y equals 0. And the reason for that, let's think about why that is. What we're saying is this function will never be 0. That should make sense, because remember, b is a positive integer or fraction. It could be a rational number. It could be any real number. It's a positive real number, and it's taken to a power. Whenever we take any number to a power, we'll always get something positive, and because it was positive to begin with, and we'll always get something non-zero, because you'll never make that value 0. So your horizontal asymptote is at 0 no matter what your b value is. So that's the first characteristic that you want to write down about exponential functions. The second characteristic has to do with a very key point that we just noticed here, 0, 1. No matter what your b value is, if you plug in 0, you will always get 1. Any number like 3 to the 0 power is 1. 3 halves to the 0 power is 1. These are always going to be equal to 1. Again, it's as long as this box right here is a positive real number that's not equal to 1. So these are two key characteristics that you need to know. So what we're going to do is use those two key characteristics to graph our function. We are going to have to make a table of some other values in order to make a complete graph. But the number one thing that most of us will forget is the horizontal asymptote. So let's take a look at this first example and talk about what this one will look like. F of x equals 3 to the x plus 1. 3 to the x plus 1. So the first thing is it's going to have a horizontal asymptote at 0, because this function right here, 3 to the x plus 1, can never equal 0. So that's the first thing I'm going to add to my graph. Horizontal asymptote. The next thing, the thing that we didn't really talk about, that there was such commonalities in these graphs, notice again that these graphs, that some of them are going downward, namely these guys were all going downward, and some of them were going upwards. These were all going up. So with these functions, we have interesting characteristic of when do they go down and when do they go up. Maybe you did or did not notice this, but the blue ones all have b values that are smaller than 1, but of course bigger than 0. They were all fractional values. This b up here was 1/4. The other b was 1/3 and 1/2. They all had b values that were smaller than 1. The b values for the other ones were when b was greater than 1. So when b is between 0 and 1, it's going to be a decreasing function. It's going to slowly get smaller and smaller. These will be our decaying functions when we're talking about something decaying. And you'll see a lot of those. Maybe you remember the corpse problem from last year. When b is greater than 1, that was the functions that were going upwards. Those are increasing. Those are when b is greater than 1. That's going to be like our interest rate. We're gaining money every year, so of course we're going to have our interest rate is going to cause our account balance to go up over time. So with that, we want to remember that our function for this one, the one that we're doing the example over here, the 3 to the x plus 1, that's of course going to be an increasing function because 3 is bigger than 1. So I know it's going to be increasing. So the next thing that I do is I start to think about the key point that when x was 1, x was 0, y was 1. That key point. Now that key point only works when my function, remember the function was b to the x. Now we have 3 to the x plus 1. So let's think about what this means for my graph of 3 to the x plus 1. We know it's increasing, but we want to figure out where that 0 value is. So what we're going to be looking at is we're going to be asking the question, 3 to the x plus 1, when is this value 0? The one value you have to think about carefully. When is that value 0? Well, that value is 0 when x is negative 1. Why is that so nice? Because if I plug in negative 1, I can quickly calculate in my head that this answer, it would be 3 to the 0, which is 1. So I just found one value in my table. When I plug in negative 1, y is 1. So here's one value in my graph. Once I have one value in my graph, I'm just going to plug in 2 more points just so I can sketch this graph. I know it's increasing, but I'm going to quickly plug in 2 more points on either side. So I'm going to plug in negative 2, and I'm going to plug in 0, because that's the one to the right. So plugging in 0, I get for my function 3 to the 0 plus 1. I get 3 to the first power, which is 3. So at 0, I get 3. Plugging in negative 2, f of negative 2 is 3 to the negative 2 plus 1, all in the exponent, of course. So that's really just 3 to the negative 1. And hopefully you're remembering negative exponents. When we have a negative exponent, we really just have the reciprocal. It's really just 1 over 3 to the first power. These are equivalent statements because that's what a negative exponent is. So when I plug in negative 2, I get 1/3. So that fits with my idea of decreasing to the left and increasing to the right. So this is where my final point is. And it looks like it's really close to 0. And I sketch my graph in the nice curve that's increasing. And you're done. So remember we found the one point when the exponent was 0 because that's an easy point to do in our head. Let's take a look at another example and what happens with this one and how it's slightly different. So our next example is 2 to the x minus 3. So this one again, we want to remember about our horizontal asymptote. But our horizontal asymptote really describes the exponent value. 2 to the x will never equal 0. Okay, so this circle is going to get really close to 0 but never equal 0. So what this minus 3 does is it shifts the graph down 3. Okay, so my horizontal asymptote is no longer at 0, it's at y equals negative 3. So for this graph, we have a horizontal asymptote at negative 3. And again, that's because the 2 to the x will never be 0. It'll get really close. So when it gets really close to 0, let's say it hits 0, minus 3, negative 3 is the value that it'll get really close to. Now my next thing I want to do is think about when the exponent is 0, because that's the next key point that's going to be easiest to find. Well, in this case, it's when I plug in 0. So I'm going to plug in 0 and find that one point because I know it's going to give me a nice value. F of 0 is 1 minus 3 or negative 2. So 1 minus 3, negative 2. So F of 0 is negative 2. So here's my second point. I mean, my first point. Now again, I'm going to plug in points on either side. So I'm going to plug in, and you don't have to plug in points on either side. You can plug them both in. So let's try that. Let's plug in F of 1 and F of 2 just to see what we get. So F of 1 is 2 to the first minus 3, which is 2 minus 3 or negative 1. So at 1, it's negative 1. And then F of 2 is 2 to the second minus 3, or 4 minus 3, which is 1. So F of 2 is 1. So there I see my increasing curve. I always want to plug in those 3 points and find my horizontal asymptote. Okay, so to summarize the graphing, the first thing is to find the horizontal asymptote. The second thing is to find where the exponent equals 0. That's always your starting point, and then you'll be able to graph some points nearby, like we did twice now, to find the other values. So let's try this one more time. Find the horizontal asymptote for this final function. 2 to the x, negative 2 to the x minus 1. So the first thing we want to do is think about the horizontal asymptote. So again, it's this value right here. Will this ever be 0? So careful notation with this. This says negative 2 to the x minus 1. So we really would calculate the exponent and then throw a negative on this. So this value actually will always be negative. This does not say negative 2 to the x minus 1. That is not an exponential function. What was listed here is different and is an exponential function. This simply says find 2 to the x minus 1 and then throw a negative on it. So everything's going to be in the negatives. So let's graph this function. Again, this red function will never be 0. Okay, so my asymptote is still at 0 on this case. There was no shifting like we saw above with 2 to the x minus 1. So we're going to have an asymptote at 0. Now we're going to simply figure out when the exponent is 0. So when is the exponent 0? We'll figure that out by looking for when is x minus 1 0. Well, that's when x is 1. So I'm going to plug in 1 because that's when my exponent will be 0. And I get negative 2 to the 1 minus 1. Okay, so again, we do the exponents first, and we're going to do negative of 2 to the 0 power. Again, we do 2 to the 0 power first, and we get negative 1. Okay, because 2 to the 0 is 1, and then we throw the negative on it. So we get negative 1. So my first point that I'm going to graph is at 1, negative 1. 1, negative 1. Now I'm going to plug in some points around it. This time I'm going to go on either side again. So remember we just plugged in 1 for x. Now let's plug in 2 and 0. So we're going to find 2 more values, f of 2 and f of 0, and see what we get. F of 2, opposite of 2 to the 2 minus 1, opposite of 2 to the first power, which is just negative 2. So 2 gave me negative 2, so I'm going to go over 2 down to negative 2. F of 0, that is the opposite of 2 to the 0 minus 1, which is opposite of 2 to the negative 1 power. Remember, negative exponents is really just the reciprocal, so it's going to be negative of 1 over 2 to the first power, which is negative 1/2. So at 0, I'm at negative 1/2. Do you see your curve forming? It's a true flip of the regular exponential function. So instead of increasing, it's going to shoot off to negative infinity, and it's always negative. So that's another key characteristic you're going to be looking for. This negative flips the function. So there are some things to think about here, but as you get more practice, really it's just plugging in the 3 points, and it should be simple once you find when the exponent is 0 and the horizontal asymptote. Okay? And the horizontal asymptote is only affected by a shift. So you're going to give these 2 questions a shot. For this chapter, we'll always have 2 checkpoint questions. One will be a multiple choice question, MCQ, and one will be a free response question, FRQ. And you will always enter them in the same Google Doc, so it'll constantly be the same exact Google Doc. Make sure you pick the proper video. This video that we are just watching is 3.1.1. So answer the following questions. The first one is kind of a review of what you did in class on Wednesday and Thursday. And the second question, the free response, is really trying to help you see if you understood from this video. And you'll be using the following function. F of x equals 4 to the x minus 1 plus 5. See if you can find that key information, the horizontal asymptote, and 2 key points you would use to graph this function. See if you can find 2 of those key points. Maybe you can even find 3. But describe what those key points are and what the horizontal asymptote. Bring those questions into class, and good luck, and we'll see you in class. See you in class.